everyone. In this video, we are going to discuss about the periodic trends in properties of elements from the chapter 3 classification of elements and periodicity in properties, class 11 chemistry. See, we will be discussing about the trends in physical properties, that is especially the periodic trends with atomic radius in this video. We will be discussing about the periodic trends with ionization enthalpy, ionic radii, etc., electron gain enthalpy, etc. in our coming videos, which will be available in the playlist. You see, within a period, the chemical reactivity tends to be high in group 1 metals and lower in elements towards the middle of the table and increases to a maximum in the group 17 non-metals. Within a group of representative metals, say alkali metals, the reactivity increases on moving down the group. Within a group of non-metals, say halogens, reactivity decreases down the group. So why do the properties of elements follow such trends? To answer this question, we should know the periodic trends in physical properties and chemical properties. So in this video, we will be discussing the trends in physical properties, that is periodic trends with atomic radius. See, there are numerous physical properties of elements such as melting point, boiling point, etc. which show periodic variations. However, in this video, we will be discussing about the periodic trends with atomic radius first. Periodic trends with respect to ionic radii, ionization enthalpy, electron gain enthalpy and electronegativity will be discussed in the coming videos, which will be available in the playlist. So you see, let us talk about the atomic radius of elements. See, finding the size of an atom, it is a lot more complicated process. The size of an atom is very small. It is approximately 1.2 angstrom in radius. 1.2 angstrom means 1.2 into 10 raised to minus 10 meter in radius. See, the electron cloud surrounding the atom does not have a sharp boundary, so the determination of the atomic radius cannot be precise. An estimate of the atomic size can be made by knowing the distance between atoms in the combined state. That is, consider a non-metallic element. See, what we are talking here will be suitable for all other non-metallic elements. So, for a non-metallic element, say chlorine is a non-metallic element. To estimate the size of the atom, that is for non-metallic elements, to estimate the size of the atom, we just want to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule. That is, for chlorine molecule, Cl2 molecule, the chlorine, the bond length is 198 picometer. Pico means 10 raised to minus 12. Okay, so 198 picometer means 198 into 10 raised to minus 12 meter. Now you see, so here for a chlorine molecule, the chlorine bond length is 198 picometer. So half of this distance is taken as the atomic radius of chlorine. That is, half of this distance 198 picometer is actually 99 picometer. So this value is actually taken as the atomic radius of chlorine. More specifically, we can say that it is the covalent radius of chlorine. That is, if the element is a non-metal like chlorine, the term atomic radius refers to the covalent radius of an atom. See, atomic radius or van der Waals radius, that actually represents the overall size of an atom. So, atomic radius, that is the distance from the nucleus to the outermost electron in an atom. And you see, covalent radius, it is the distance between two atoms of the same element in a covalent bond. So, covalent radius is the distance between two atoms of the same element in a covalent bond. So, here we have chlorine covalent bond. So, both are same elements. So, distance between these two chlorine atoms in the covalent bond, that is actually the covalent radius of chlorine. And covalent radius actually represents the size of an atom in a covalent bond. Now, for metallic elements, for example, let us consider a metal copper. For metallic elements, that is, if the element is a metal, the term atomic radius refers to the metallic radius of an atom. Okay, see, for if the element is a non-metal, the term atomic radius refer to the covalent radius of the atom. For metallic elements, that is if the element is a metal, the term atomic radius refer to the metallic radius of an atom. For a metal, the metallic radius, it is actually the half the internuclear distance separating the metal cores in the metallic crystal. That is, for a metal, the metallic radius is actually half the distance between the two adjacent atoms in a metal crystal lattice. So, for a metallic element, the term atomic radius refer to the metallic radius of the atom, and metallic radius is actually half the distance between two adjacent atoms in a metal crystal lattice. That is, for example, the distance between two adjacent copper atoms in a solid copper is 256 picometer. So, its metallic radius will be half of this value, that is 256 picometer divided by 2, which is equal to 128 picometer. So, this is the metallic radius of copper. See, metallic radius represents the size of an atom in a metallic bond. A rough estimate of the relationship between atomic radius, covalent radius and metallic radius is atomic radius is greater than or equal to covalent radius, which is greater than or equal to metallic radius. See, the values of the radii of atoms are not fixed values. They can vary depending upon the specific element, bond type, crystal structure, etc. For example, the atomic radius of sodium is 186 picometer. This is the atomic radius of sodium. Covalent radius of sodium, that is in the covalent bond, the covalent radius of sodium will be 154 picometer. That is when sodium atom forms a covalent bond with another atom, the radius of sodium atom will be 154 picometer. That is the distance between sodium nucleus and the shared electron pair. That is actually the covalent radius for the sodium atom in the covalent bond. That will be 154 picometer. And the metallic radius of sodium atom, that is actually equal to 191 picometer in a metallic crystal lattice. That is, when sodium is in its metallic state, forming a crystal lattice with other sodium atoms, the distance between the center of one sodium atom and the center of its nearest neighboring sodium atom is 191 picometer. In our classes, we will use the term atomic radius to refer to both covalent or metallic radius, depending on whether the element is a non-metal or a metal. See, the atomic radius can be measured by X-ray or other spectroscopic methods. See, the atomic radii of a few elements are listed in this table. This is actually for the second period elements: lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. Their atomic radius in picometer are also given here. So by analyzing this, you can see that lithium is the leftmost one, fluorine is the rightmost one in the second period elements. So as we move from left to right of the second period of the periodic table, we can see that the atomic radius or the atomic size decreases as we move from left to right, that is across the period of the periodic table. See, this can be explained using nuclear charge and energy level. That is, atomic size generally decreases across a period. It is because within a period, the outer electrons are in the same valence shell. That is, for example, if you consider the second period element lithium, its atomic number is 3. So, its electronic configuration 1s2, 2s1. Okay, so here the principal quantum number is 2. For beryllium, the outermost principal quantum number is 2. For nitrogen, That is, the outer electrons are in the same principal energy level. That is, here principal quantum number n is equal to 2, which corresponds to the L shell. So, all the outer electrons are in the same shell, that is L shell. They have the same principal energy level with n is equal to 2. You see, the atomic number increases from left to right, because you see 3, 4, 5, 6, 7, 8, 9, no, atomic number increases from left to right. So, the positive charge of the nucleus increases, which pulls the electrons closer. So, atoms become smaller, atomic size decreases. That is, within a period, the outer electrons are in the same valence shell, and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Now let us see the variation of atomic radius with atomic number across the second period. So you see, when you consider across the second period, for lithium, its atomic radius is 152. Okay, so for lithium, atomic number 3, atomic radius 152. So somewhere here we get a point. That is, it is actually a plot of atomic radius in picometer versus the atomic number. Then the next element is beryllium. Its atomic number is 4 and its atomic radius is 111. So 4, 111 somewhere here. It's a rough estimate, okay. Then for boron, atomic number 5, atomic radius 88 picometer, so somewhere here. Carbon atomic number 6, atomic radius 77, somewhere here. Okay, nitrogen atomic number 7, atomic radius 74, somewhere here. Similarly, you will get the points for the other elements too. So when you join all these, you see, you will get a graph like this. So this graph actually shows the atomic radius in picometer versus the atomic number of elements. This is actually for the second period elements. You see, there are some exceptions in this case. That is, for transition metals, that is D block metals, atomic radius remains relatively constant or increases slightly. And for lanthanides and actinides, that is F block elements, atomic radius decreases with irregularity. So some exceptions are also there. Now you see, within a group or family or vertical column of the periodic table, the atomic radius increases with atomic number. So across a period, atomic radius decreases with atomic number. But within a group, that is, as we move down the group, the atomic radius increases with atomic number. You see, the atomic radii of a few elements are listed here. This is actually for the group 1 elements. Okay, here we have lithium, sodium, potassium, rubidium and cesium. Their atomic radius in picometer is also given here. Electronic configurations are also written here. So from this you can understand that for lithium, its outermost principal quantum number is 2. For sodium it is 3. For potassium it is 4. Rubidium it is 5. And for cesium it is 6. That is, as we descend the group or move down the group, the principal quantum number n increases. Okay, and the electrons are farther from the nucleus. This happens because the inner energy levels are filled with electrons, which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. That is, as we move down the group in the periodic table, the principal quantum number n increases. See, 2, 3, 4, 5, 6 principal quantum number n increases, and the distance between nucleus and the outermost electrons increases. Inner electrons shield outer electrons from the nuclear attraction, which reduces the effective nuclear charge, and hence the atomic size or radius increases. Now let us just plot a graph of atomic radii in picometer versus the atomic number. That is it. This graph actually shows the variation of atomic radius with atomic number for alkali metals. Okay, group 1 elements we are choosing for alkali metals. So for lithium, its atomic number is 3. Its atomic radius is 152. So 3 will be somewhere here, 152 somewhere here. We get a point here. Then for sodium, atomic number 11. Atomic radius 186. So somewhere here, 11, 186. It's a rough estimate. Okay, for potassium 231, so 19, 231 somewhere here. Rubidium 37, 244, so 37, 244 somewhere here. Cesium 55, 262, so somewhere here. So when you join all these, you will get a graph like this. Okay, so in this video we have discussed about the periodic trends with atomic radius. I hope it is clear to you. Thank you.